All right, so in this video, we are going to recapitulate what we have discussed about ionic compounds in class. Okay, so let's see the ionic compounds. So the first thing we did was we discussed the differences between ionic compounds and covalent compounds. Okay, so we have ionic versus covalent. Those are the two classes of compounds. And examples for ionic compounds are sodium chloride, magnesium oxide, calcium carbonate, and so forth. And examples for covalent compounds are carbon dioxide, H2O, nitric oxide, and so forth. Now, immediately we can see that the covalent compounds only contain non-metallic elements. Okay, but when it comes to ionic compounds contain non-metallic elements as well as metallic elements. So they're okay. So if we have a metallic compound, a metallic element in a compound, most likely that compound is an ionic compound. Okay, and the idea is the ionic compounds are actually made of cations and anions. Okay, made of cations, which are positively charged ions, and anions, which are negatively charged ions. So that's what ionic compounds made of. Mostly these cations are metallic elements most of the time, but there are non-metallic complex or multi-atomic cations as well, which we're going to discuss later. But if we have a metal, that metal will have a positive charge in ionic compound, therefore they are called cations. And the anions are the non-metallic part. So non-metallic part usually has higher electronegativity, and as a result of that, they're going to grab the electrons away from the metal, giving and making them have a negative charge. That's why they have they are the anions in an ionic compound. Okay, now the other difference we discussed in class here was the submicroscopic representation. Okay, microscopic presentation. So we discuss how in covalent compounds. So let's take an example like say H2O or carbon dioxide. Doesn't matter. So if you think about H2O, okay, in H2O we are going to have discrete molecules. Discrete molecules, right? So we're going to have the oxygen and then the hydrogens. Okay, oxygen, hydrogen, oxygen, hydrogen, oxygen, and hydrogen, and so forth. But on the other hand, this is H2O. Okay. On the other hand, if you consider a submicroscopic representation of an ionic compound, let's think about magnesium chloride. Okay, so that means we have one magnesium ion and then two chloride ions in this compound. So in this case, we do not have molecules. We do not have discrete molecules. Okay, instead, what we're going to have here is we are going to have the positively charged species or positively charged cation. Okay, and then we're going to have negatively charged anion. Okay, so every one cation, we're going to have two anions. So let me indicate that. Okay, we have something like that. So it's gonna continue like that. And this is called an ionic lattice or an ionic network. So one more time to summarize, in ionic compounds, what we have is an ionic lattice or an ionic network, while in covalent compounds we have discrete molecules of the compound. That's one of the main differences between ionic compounds and covalent compounds. And then what we have to deal with was the chemical formula of ionic compounds. Okay, so when it comes to chemical formula, all right, So even though we don't have molecules, okay, we still write magnesium Cl2, I mean MgCl2. Okay, so what does this mean? What this means is the chemical formula gives you the ratio between the ions or the cations and the anions in the in the compound. Okay, so if we draw magnesium chloride one more time, okay, so this is magnesium and this is chlorine, so we have two of them. So what this means is for every one magnesium you have two chloride ions. That's what it means, but one is implied, so we don't have to write one, and therefore we're going to write the magnesium chloride chemical formula this way. Okay, so this shows you the ratio between the cation and the anions. And then we're going to talk about why we need two chloride ions for every one magnesium ion. Why isn't it 1 to 1 in a bed? But before that, what we want to do is we need to be able to determine the charges of elements in an ionic compound. Okay, so let's see if we can do this. The third thing, the fourth thing we discussed in class. Okay. Charges of the elements in an ionic compound. Okay, so I want to see if I can do something here. If I can, let me see, share. All right, no, okay, it's okay. So when it comes to determining the charges of the elements in an ionic compound, all we need to know is the positioning of that element in the periodic table. Okay, so if I can have a periodic table, I'm going to actually generate one here. I mean, draw one here. So, in the periodic table, we have the first group. Okay, so we have, let's skip hydrogen for the moment because hydrogen can be weird. It can be on both sides, or metal or non-metal. But let's start with lithium. Okay, so we have lithium, sodium, potassium, and so forth. And then we have beryllium, and then sodium, magnesium, calcium, and strontium, and so forth in the second group. Okay. And then at the other extreme, we have the noble gases. Okay, so we have helium, and then we have neon, argon, krypton, and so forth. And then just before that, the group before the noble gases are fluorine, chlorine, bromine, and then we have oxygen, sulfur, selenium, and then we have nitrogen, phosphorus, and then we have carbon group. So these are the groups we have. And then we have something in the middle which we call the transition metals over here. Okay. Transition metals. Okay. Anyway, now we know that this is group 1, group 2, and then this is group 8, the noble gases. And then we have group 7, group 6, group 5, and group 4 in no Roman numerals. Okay. Now the cool thing about these numbers is these numbers tells us how many electrons they have in the valence shell. Then, in other words, number of valence electrons. Okay, so the group 1 has this 1 over here, meaning we have only one valence electron. Okay, so this 1 means we have only one valence electron. Therefore, when it is in a compound, okay, when it's in an ionic compound, it's going to have a +1 charge. The reason is it has only one electron. Therefore, removing that electron will minimize their energy, okay? Or removing that electron will make them achieve a noble gas configuration, and as a result of that, it's going to form +1 ions. For lithium, if lithium loses its only one electron in the valence shell, it's going to have the helium noble gas configuration. If sodium loses its one electron in the valence shell, it's going to achieve the neon noble gas configuration and so forth, which is more stable or lower potential energy than sodium itself. Okay, therefore group 1 is going to form +1 ions. When you go to group 2, they have 2 valence electrons now. Therefore, they have to remove 2 valence electrons to become like a noble gas. Therefore, they're going to form +2. And then we have things like, which I did not mention actually, aluminum, okay, magnesium. So somewhere on here we have aluminum, and I think and it's gallium and so forth. So if you have aluminum, it has 3 valence electrons. Therefore, in an ionic compound, they're going to form +3 charge because they have to remove 3 electrons to become like a noble gas. Okay. Now going back to the noble gases, all right. So they have the full or complete valence shell. Okay, and therefore they're not going to participate in chemistry usually. And they're going to therefore we're going to move on to the group before that, chlorine, chlorine, bromine, where we have 7 electrons. Okay, which is indicated by this number over here, 7. Okay, so if they have 7 electrons, it is easier for them to gain 1 electron and become like a noble gas rather than losing 7 electrons. Losing 7 electrons will cost them a lot of energy. So instead, they will gain 1 electron and become like a noble gas. If they gain 1 electron, they're going to gain a negative charge. Therefore, they're going to have the -1 charge. Okay. If you move one over, oxygen, sulfur, selenium, they are going to have 6 valence electrons. Therefore, they need to gain 2 electrons to become like a noble gas, forming -2. Nitrogen, phosphorus, they need to gain 3 electrons, okay, because they have 5 valence electrons to become like a noble gas. They need to gain 3, and something like carbon in an ionic compound will form -4 because they have to gain 4 electrons to become like a noble gas. Okay, so just by looking at the periodic table, we are able to determine the charge of these elements in an ionic compound. Now, I know that I skipped some of the elements in the middle called transition metals. So transition metals, the reason I skipped them is they can form various charges. Okay, so because of the involvement of the d electrons, which have comparable energies, they can form different charges. Okay, I'll give you an example. If you take something like, say, iron. Okay, iron, we can denote iron as Fe. So Fe can form an ionic compound with oxygen. Okay, it can form FeO, or it can form Fe 2O3, or it can form FeO2, and so forth. Okay, now we know the oxygen can have only 1 charge, that is -2, because that is 2 groups away from the noble gases. In other words, oxygen has 6 valence electrons. Therefore, oxygen would gain 2 electrons to become like a noble gas, so it's going to have a -2 charge. Okay, but so if you consider the first compound over here, FeO, so oxygen is -2. Therefore, Fe has to have a +2 charge in an ionic compound, because I think the thing about the chemical formula of ionic compound is it is always neutral, charge neutral. It shouldn't have a charge, overall charge. Okay, if we have a -2 on the anion side, okay, then we need to have the opposite positive charge on the cation side, which is going to be +2. Okay, so here our our Fe will have +2 charge. Okay. Now on the other hand, if we take Fe2O3, again oxygen is -2. You have three of them. That means our anion side should have a charge of -6. Okay. Therefore, our cation side, which is Fe2, should have a charge of +6. Okay. So our entire cation side has a charge of +6. Therefore, one Fe ion should have half of that charge, which is +6 divided by 2. It's going to be +3. On the other hand, if we go to FeO2, right? Again, oxygen is -2. You have two of them. Therefore, the anion side will have a -4 charge. Okay. That means our cation side should have a +4 charge. Therefore, in FeO2, the charge of Fe is +4. So you can see that the same element Fe is forming different charges depending on depending on what the compound is. Okay, for that reason, we need more information whenever we are given a transition method to decide their charges. Okay, and also in some cases you will see that you will get information like, say, like copper within parentheses 1. Okay, if we have this, what this means is we have copper plus ions. Sometimes we might have copper within parentheses 2. Okay, so this means we have copper 2+ ions. All right, so that is about how to determine the charges of the elements in an ionic compound. All right, so with that, what I want to do is I want to talk lastly about the chemical formula of ionic compounds. That's the 5th thing. Okay, the chemical formula one more time, or the charge neutrality. Charge neutrality. Okay, meaning when we have ionic compounds, the overall charge is neutral. Okay, I'll give you an example. If sodium solid combines with Cl2 gas to form an ionic compound, with sodium solid, we're going to get sodium atoms. With Cl2, we're going to get Cl atoms, right? You notice that even though we have Cl2, we don't bring Cl2 as it is. We just bring the atoms of Cl. Okay, so we know that sodium is going to always form +1 in an ionic compound. Chlorine is going to form -1. Therefore, in an ionic compound, if they combine, they're going to combine 1 to 1. Sodium 1, Cl1. So the ionic compound chemical formula should be NaCl. Similarly, if we take something like magnesium, let's say magnesium. Okay, magnesium solid combining with, say, a fluorine gas. Okay, so with magnesium solid, we're going to get magnesium atoms. With fluorine gas, we're going to get fluorine atoms. And the magnesium will always form +2 because it has 2 valence electrons, and fluorine will always form -1. Therefore, when they combine to make magnesium 2+ neutral, you're going to need 2 fluoride ions to neutralize this magnesium 2+. Okay, so the chemical formula would be MgF2. Let's do another one. This time, let's do aluminum sulfide. Okay, aluminum solid combining with, say, S8 solid. Okay, so from aluminum solid, we are going to get aluminum atoms, and then from S8, we're going to get sulfur atoms. Okay, aluminum will always form +3 because it has 3 valence electrons, and then sulfur will always form -2 in an ionic compound. Therefore, when they combine to have a neutral compound, they need to form Al. It's going to have Al and sulfur. So they're going to have 3 sulfur and then 2 aluminum ions. Okay, and how did I get this number? Okay, just to show you a trick, all I did here was I used the charge of the cation as the subscript of the anion, and I used the charge of the anion as the subscript of the cation. Okay, when you do that, you can see that that we're gonna achieve the charge neutrality. Let me show you how. Sulfur is -2. If you have 3 of them, the anion side will have -6. 3 times -2 is -6. And aluminum is +3. We have 2 of them. Therefore, 2 times +3 is +6. Okay, guess what? +6 plus -6 is 0. Okay, and that's why Al2S3 is our chemical formula for this. All right, I think that covers, that actually recapitulate what we have discussed in class about ionic compounds so far, introduction to ionic compounds. And then in our next video, we will talk about the properties of ionic compounds, how to predict them and how to explain them, properties such as solubility in water and then melting temperature of ionic compounds. All right, bye everybody.